Looks like we're ready. Hello, good evening, everyone. So those of you who don't know, I'm Tapan Saha. I'm a professor of electrical engineering at UQ. I'll be your host for this evening. So before I start the formal introduction of my speakers, I would like to acknowledge the traditional owners and their custodianship of the lands on which we meet today and pay my respect to the ancestors and their descendants who continue cultural and spiritual connections to the country. We recognize their valuable contributions to Australian and global society. Before I move further, can I please request all of you to keep your mobile phone silent, please? And then the other thing will be safety instruction. If we have some alarm coming, I will be advising you, and then you will all follow me. We'll go this way out, and then we'll gather at the Great Court just on the right side of the building of Abel Smith Lecture Theatre. And the toilets are outside. If you go out on the left side, both male and female toilets are located. And after the presentations, we will have some refreshments will be served just outside this lecture theatre. Again, we'll be going out from the top. So now let me talk about a little bit about the presentation today. So on behalf of Professors Andrew Garnett, Peter Ashworth, and myself, and in conjunction with IEEE, Power and Energy Society, their banner is here, of Queensland chapter, we are delighted to welcome you to UQ Energy Initiative Energy Express seminar. Now, just to introduce the topic, I'm sure all of you know by now that Australia is leader in distributed energy resources. With more than 2 million customers now have rooftop solar PV installations. And of them, Queensland has the highest per capita household rooftop solar PV in the world. So yes, definitely this growth is going to continue for the years to come. And also now we can see medium scale and large scale solar PV penetrations, in particular in Queensland and other states as well. Definitely this is bringing a lot of opportunities for the customers and challenges for the network to maintain the power systems, reliability and security. So we'll be talking about both issues. In fact, we'll be talking about all three issues this evening to address the issues of better home energy management systems and the variability and intermittency of the solar PV and wind power. We all know that battery can play a major role. So we have tonight three speakers who will be sharing their expertise with the battery technology and their applications from three different angles, which is our fourth presentation for 2019 in this Energy Initiative UQ seminar series. So first I will be introducing just three speakers, and then they will be continuing their presentations, 15 minutes each. I will not be interfering them. And then I will come back with my Q&A session with them. Hopefully you will be participating that time. So my first speaker this evening will be Mr. Paul Liddell. He is the Chief Technology Officer, Redback Technologies. And his presentation will be, batteries are half the answer. So you will see the name suggests something, right? So Paul is one of the founders of Redback Technologies and Queensland's own smart inverter company. Apart from 8 years of the renewable industry experience, Paul spent 9 years in Seattle working for Microsoft and has degrees in computer science and electrical engineering. Let us welcome Paul. Our second speaker will be speaking on low voltage and distribution networks. So Stephen Richardson, he's from Energy Queensland, and his presentation will be Energy Queensland experience using battery storage to support network supply. So Stephen is working on enabling new technologies to support Queensland energy users. One of the most significant roles he has been playing in this role as the project director for the grid utility support system. Many of us know that is called GAS. The deployment of 2 megawatt hours of grid commercial battery systems across rural Queensland in 13 locations. And he has worked for over 10 years on utility scale energy storage, integration, and stand-alone power systems for large and small communication sites. Stephen has a strong engineering knowledge coupled with extensive data science and analytics mindset to deliver data-driven design and system monitoring solutions. Our final speaker this evening will be Mr. James Lindley, and his topic will be battery storage in the Australian national electricity market. So he'll be talking about the large scale. So James has been with the Australian energy market operator for the last 13 years. He's group manager in system capability, and he has expert knowledge in marginal loss factors, reliability, and emerging reserve trader and frequency control in the national electricity market. James has a Bachelor of Engineering in Electrical Engineering and a Master's in Electricity Market, both from the University of Queensland. I think with that, I have enough introduction for the speakers. Now let me call Paul to come and speak on batteries are half the answer. Thank you.
Thank you, Tapan. Can people hear me okay? Great. Just let that start up. Just thinking about it.
You want me to just have a quick reset?
Okay, it's awake now. All right, thanks for having me here today. As Tapan said, I'll be talking a little bit about the behind-the-meter energy storage market and some of the promises that we have, as an industry, have been making, and how we're going in terms of meeting those promises. So just a little bit about Redback to start with, for those who are not familiar. We're a Queensland company. We're based at one of the UQ campuses over there in Long Pocket, about 10 minutes from here. And one of our big goals in starting the company was to basically maximise the penetration of DER in the grid. And we realised early on, to be able to do that, you needed to provide behind-the-meter storage. And so we set about designing a system that would enable us to put lots of behind-the-meter storage into the markets and control that storage. So our product, the core product that we sell as part of that market, is it's an all-in-one system that allows, it basically fits right in the middle of the residential PV market. Most people installing today 5 kilowatt systems. That's the single phase maximum that you're allowed to install. And so our product is targeted right at that. What we're seeing today with the installs is that people are tending to maximise their systems. And you can put in varying levels of battery storage in the unit between 5 kilowatt hours and up to 14. And it's got the capability of providing backup. And also we do spend a lot of time working on optimization. And so we've got a lot of analytics and stuff going on in the background. All of the devices are always connected to the cloud, so we can analyze the data coming in and perform optimizations on how the system's running. I'll talk a little bit more about where we could be doing more there in a few minutes. So the Redback fleet at the moment, we've now just passed, in terms of addressable, what we can control at the moment, just over 5 megawatts and more than 5 megawatt hours of storage. And what, as I was mentioning before, what we're seeing with most of our customers is that they're installing, with a 5 kilowatt system, over 6 kilowatts of PV, so they oversize the PV. And the average battery sizes that are going in at the moment are between 5 and 10 kilowatt hours, usually 5 or 10 with our system, but industry-wide we think the average is around 7 kilowatt hours of storage with a residential system. That, for our Southeast Queensland customers, to give you some idea, I just did a little kind of quick assessment yesterday of about 20 systems down near the Gold Coast in the kind of southeast corner of Queensland. And what we're seeing at the moment, because of this time of year, is about 90% self-use. And so they're really not relying on grid much at all. But they're all also exporting for large chunks of for the afternoon. We're also active working with the industry on some of the kind of industry-wide initiatives that are going on around VPP and demand response with the battery programs. And there's some other work at the moment that we're involved with ANU and Energy Queensland around setting network parameters for DER devices to make sure that they're not negatively impacting the grid. So the Battery Promises Scorecard, we've been talking about storage for a long time, and I just wrote down quickly a few of the things that we've been telling everybody that storage can solve, and some idea of how we're going as an industry. This is not about Redback, this is about the industry as a whole for behind-the-meter storage, how we're going in terms of meeting those promises. I don't have a huge amount of time here, and any one of these line items could easily take up half an hour, so I'm just going to skip through a couple of them, and then I'll go into a little bit more detail on some of the network stuff. So increased self-consumption, I just talked about that. Pretty much every system, no matter who's providing it, that has a decent-sized battery above, in the range I was talking about, 7 kilowatt hours, at the moment they're meeting that promise of self-consumption, and that's one of the core value propositions that we put to consumers. That is, you've got this big PV array on your roof, stop exporting all of it to the grid and then importing energy in the evening, and just store that energy, use it in the evening, and then you'll get a positive economic outcome because you're playing that arbitrage between your export at 8 or 9 cents and buying energy at 30 cents in the evening, and you get to feel good because you're using your own energy. So as an industry, I think we're on track for that goal, and most people who've bought systems can feel good that they're sort of getting that in the current state. Backup depends on what system you buy. A good chunk of the systems are AC coupled versus PV and battery all on the one line, but nevertheless, backup options are available across the industry. And so if it's something that a consumer wants, then they can tick that box. They usually spend a little bit more money to, obviously you wire certain circuits for backup and others for not. Whole house backup's quite expensive. So people tend to pick just a few critical circuits. But again, as an industry, we can say, yes, we're providing that service well. The next one is competitive return on investment compared to solar alone. That's a tricky one, and I would say there are definitely cases where we're there already today, and there are cases where we're not. The industry hasn't gotten to a point where there's a single kind of product offering that you can look at and say, this is a canonical product. The prices vary massively for a system between somewhere around $10,000 or $11,000 up to $25,000, depending on which manufacturer and what bells and whistles you've signed up for. Obviously, those bigger systems, the more expensive systems, are quite difficult to prove an ROI in 10 years. But the less expensive ones, you're actually in a position where you can definitely show an economic benefit over the lifetime of the system. And that's compared to solar alone, and even more so compared to not having a system on the house. So I'd say we've got a lot more work to do in that area, but battery prices are coming down and we're getting better all the time at finding other avenues to reduce the system costs. So there's been some subsidies, but we've got VPP and all kinds of other things going on. I think I better speed up. So I'm just going to skip through the next one for network operator, which is provide ancillary services. There's a huge amount that's been said on this topic and could be easily a topic for an entire presentation. There's lots of requirements for the network for frequency response services, demand response, and then just basically trading at the wholesale level with batteries and with fleets of batteries. And the state at the moment of that is that we're going into trials. And there's lots of trials going on, but none of them are yet at the scale where they're really able to have grid impact, but we can see what they're going to do. So we're kind of on our way on that one. And the next two are the ones that I want to spend a bit more time on. So I'll just skip across to other parties and say, energy retailers are interested in VPP. We work with Energy Australia on a VPP ourselves. And we've got housing developers who are starting now to move into a state where they're requesting that all the houses or a percentage of houses in a subdivision will all have behind-the-meter batteries. And the reason for that is some of them want to run their own VPPs. And then the other reason is that there are a number of them that want to reduce the connection cost. Because if you've got batteries behind the meter, then you can reduce the size of the pipe that has to come in from the network. And then that can be quite a dramatic infrastructure cost reduction for a subdivision, for example. And so we're actually seeing a lot of interest from developers in that area. Now I'm going to dig in a little bit to this, these other two, which I've got in here, which is the promise of flattening the solar duct curve and addressing voltage rise on LV feeders. So the duct curve, I think probably people in this room are mostly familiar with it. I'll give you a lightning fast version of it. Here's a simple load curve for regular day. You can see you have a dip. I don't know if I've got a laser pointer here, maybe. Here in the morning, and then it gradually builds through the day. You've got a peak in the evening when people come home, turn on their air conditioners. So the duct curve is this negative solar curve imposed on that. That's basically showing what happens when you have a huge amount of solar on the network that's uncontrolled. And the problem with this, oops, gone too far. The problem with this is this ramp here. Whoops, I'm one too far again. Here we go. The ramp here is the problem because you have to ramp from this low point of load up to the maximum in a very short period of time, over a few hours. And it's very difficult for the embedded fossil fuel generators to do that. And so one of the promises that we made with putting lots of batteries on the network is that we'd be able to address this. So this is what the curve should look like once you've got a bunch of smart battery storage on the network. Now what you can see happens here is you start charging the batteries at, as the PV peak is coming in, and that shaves off, so the trough in the load isn't quite so much because you're charging your battery in this point here. And then in the evening when people come home, air conditioners come on, you discharge your battery. And so you get this much nicer orange-shaped, less aggressive-looking duct. And that's your improved duct curve with PV, with battery storage. However, let me show you one of our systems from the other day. So what you're seeing here is the battery state of charge. You've got your nice gold PV curve, and this grey line here is your grid export. You can kind of ignore the step in it. That's just a different charging profile. But the interesting thing here is we reach basically 100% state of charge at 9:30 in the morning. So then if you look at the other thing that we were talking about, which is voltage rise on the LV networks, your maximum PV export is still happening in the middle of the day. And so actually, you're not really improving the worst case for the grid for voltage rise. You're still, I'll show you the next slide, you're still getting this improvement here as you discharge your battery in the evening, so that's great. But what you would end up happening if all the batteries are behaving similarly is you actually make this part of the curve worse. Because you're charging your battery up as the sun comes up, and they all reach complete battery within about an hour, and then they go from 0 to 100% export over a 10-minute period per battery. You get some diversity there, so that might happen over an hour. But you end up with this pretty significant issue here, and that's happening with the default battery charging profile. The default battery charging profile, what I've called selfish charging down there, is just optimized for personal economic benefit for the household. That's the default profile you see across the entire industry at the moment. So obviously the concern there is that we could end up exacerbating the problem that's in the network if we're not careful. Now, we can do this and create a nicer curve, but today that isn't happening by default, and so it's work that has to happen. What do we have to do to make that happen? Well, you need to optimize your charging profiles. And to do even like a good job on basic battery charging, you need to know what your system size is, what your general generation profile is, your general load profile, so that you can then predict what it's going to be for the current day. You need to know the weather. And then you can set a charging profile that makes sense for the day ahead. You still need to be careful about optimizing for the consumer, because if you've got a sunny day in the morning and cloudy in the afternoon, then the default charging profile is the right one. But if you don't have that scenario, then actually you want to start charging later, and you want to charge at less than your maximum charging capability. And so that is kind of a minimum bar that we need to get to as an industry to make sure that we're actually doing the right thing by the networks when we put these batteries on. Even if everyone moves to 14 kilowatt hour batteries, they'll all be fully charged by lunchtime on a good day. And so there needs to be, today there's no sort of incentive to get you to change the operation of the systems. And of course, it's more complicated to set up an intelligent charging profile. There are other additional factors that I mentioned right here around network constraints. If you've got pre-programmed VPP events that are going to require a discharge during the day, and time of use tariffs that will all impact what is the optimal charging profile for that particular customer on that particular day. And so it can certainly be solved, and we've done a lot of the work internally to solve it ourselves. But it's definitely a work in progress for the industry and something to be aware of, I think, for the networks. So quick summary, for residential, behind the meter batteries, they do add value already today for consumers. For networks, they're adding some value because they are reducing that peak in the evening already, but there's definitely more work to be done to make sure that they don't make the situation worse early on in the day, and also to make sure that we do the best job we can to reduce voltage rise on the LV networks. Currently, we're not doing any harm because there's very low fleet density across the networks, but now's the time for us to start implementing those changes, because we all saw how fast behind the meter PV grew, and we're going to see the same thing in battery deployments before too long. And that's me. Thanks very much, and I'll be sticking around after for other questions. Thanks, Paul.
Look at my laptop, I have it back with 10 o'clock.
Oh, that's all right. Cool. Can everyone hear me okay? Yeah, excellent. Thank you for the opportunity to come and present tonight. So obviously, I'm going to talk about Energy Queensland's experience using battery storage to support network supply. So a little bit different to what Paul's just spoken about, but very much looking at now network-sided battery storage. How can it be used to support the network? And actually, very interesting you mentioned about the duck curve and the voltage rise, which I will touch on. How we may be able to do that in a different way using network-sided storage, but there are some challenges that come with that. So look, just really quickly wanted to touch base and let everyone, this is the overview for Energy Queensland, in that we now cover the whole state. Southeast Queensland, east coast all the way up to the Torres Straits and west to the border. We deliver about 35,000 gigawatt hours of energy, 7 gigawatt peak demand, 2.8 million customers, and the big one up the top right hand there is 460,000 rooftop PV systems and 355 megawatts, and that is growing day by day at the moment. That figure was probably about 4 weeks ago, which will be a little bit different. So Energy Queensland has been in the energy storage game now for actually a number of years. Ergon Energy Network actually has a history that goes back almost 20 years with energy storage. Now, it wasn't grid scale storage, it was standalone power systems, the big topic at the moment. And Ergon Energy used to have a business that sold standalone power systems to farms, station houses, etc. Back about 20 years ago. It closed down about 10 years ago. So that's really where a lot of our experience started, and we have just built from there as we have continued through. So we've been actively trialling the energy storage now on the network for about 10 years. As I said, we've got a geographically diverse installation base. So some of our systems are as far west as Mount Isa, as far south as St George. We have a couple in southeast Queensland. Our most northernest one is actually up at Charters Towers. So 2 hours north of Charters Towers at a place called Weir up there. And all the way out to the coast, we've got a couple in near Mackay as well. So we've got a broad, diverse area. We have battery systems that cover all market segments. We have residential batteries. We have C&I commercial. We have the rural. We have the urban. And Eureka, our unregulated arm, is actually getting into the space of big batteries. So they're putting a megawatt scale battery in Townsville as well. We have used just about every single technology, including all the new ones when it comes to batteries, inverter topologies, monitoring systems, control systems. We've basically tested all of them. We have a lab in Cairns where we basically pull the systems out of the boxes, install them, and see if they'll work without any extra effort. I don't think we've had one system go in yet where we were able to make it work without calling the manufacturer and spending about 10 hours on the phone at worst to them. And when I say we've tested everything, I mean all players in the market, we've just about had a product through. So when I'm talking in this presentation, it's not any particular supplier. We have tried just about all suppliers. The other interesting stat is that we've installed over 80 individual battery systems, which total 3.5 megawatt hours of total installed capacity, which isn't a big number these days, but 80 different installations. We have a lot of experience, a lot of war stories, you could say, of where things have gone good and where things mightn't have gone as well. And obviously the most notable is that we do have the 2 megawatt hours of our grid scale storage for Gus, which is across 20 units. So they're some of our bigger units. So grid scale storage can come in many forms. And what I've got on here are a couple of our projects around the outside, which I'll touch on really quickly. Bottom left was a trial where we were trialling renewables with battery storage to support a swirl line. That project wrapped up about 4 years ago. Top left are our Gus units. So that's 2 of our Gus units up near Taroom in central Queensland. That site is still operational today and is running really well. In the middle there is a site we've got at Eagle Farm, which is a C&I commercial industrial, where we're looking at how can we reduce the peak demand on the site, how can we support solar, and how do we actually island a full commercial site. So that site will run in island mode. We lose grid, we can change over to island, run on the batteries, run on PV, and we can transition back again. The top right one there was one of our very early grid scale storages, is a red flow system that we had very early on. We installed a couple of those, a couple being 30, about 9 years ago to trial grid scale storage at the customer's house to support the network. Big learnings out of that, and all our future projects have learned and built from that project. And down the bottom right was one of our, another residential storage system. It's a lithium system that we installed. And as you can see from the little hexagons there, we've tried all forms of technology, lithium, lead acid, flow batteries. We've had third-party integrated systems. We've had manufacturer integrated systems, large format cells, small format cells. All of them in some way have worked really well, but we've also had our challenges with them. And through all of that, there's probably not one technology that, from a grid scale storage point of view, is perfect in all cases. It's fit for purpose where you want to install them. So, for example, the 2 on the left, being in rural Queensland, survivability through fault is really important. Our Gus systems, just a really quick story. We had a system fail in November last year. It took us 3.5 months just to get a 4-wheel drive to site because we couldn't get in on the access tracks. And that system sat in a state that we knew was safe after a fault for 3.5 months because we physically could not access the site. But other systems we've had to turn out a lot faster because if we had left the system for 3.5 months, we would have been making the front page of the newspaper because there would have been a little bit of smoke coming out from somewhere that really isn't good. And the other challenge is, even with the best minds, all the experience that Energy Queensland have had, all the monitoring we do, things still go wrong. And the best designs possible that we came up with, we still managed to stuff a couple of batteries. And we stuffed them in big ways. We've had some really red spots and some paint go missing on a few trays and a few bits and pieces. We've come very, very close to some unfortunate events. However, we're learning from that. That's being fed into Australian standards, and we're hoping that that doesn't occur as we roll out into the residential market. So the meaty part for everyone. So as you can see, BESS, Battery Energy Storage System, is in the middle there. But as you can see around the outside, there's a few challenges and a few different factors that come with this energy storage on the grid. The first thing I will say is, yes, we can use energy storage to support the grid. We can also use energy storage to make the grid worse. We do both by accident sometimes. It happens regularly, but the reason is, one of those four things, it doesn't work all the time. So I'll just start with bottom right, impacts and benefits. So benefits, we have been able to prove on our swirl lines we can support the voltage. We have one installation where the volts were reading somewhere where the figure started with a 2.1 and maybe a 2.0, 100 volts-ish. Installed the 2 units, they haven't seen a voltage less than 230 volts until the units tripped off, and I was receiving phone calls daily from the local crews because the volts had gone bad again, and we were receiving daily phone calls from it. So it really helped the voltage, but the moment the battery storage tripped off, we went back to bad volts. So we had to get the systems back online. We've been able to peak load shave. One of our sites at Eagle Farm there, we're able to knock about 30 kilowatts off our peak demand. We've been doing that for over 6 months constantly. So that proves that we can do peak shaving. And solar soaking. So the duct curve you were talking about before, Paul, we, again, with the right control algorithms, with the right sensors, you can soak up that solar, but you've got to do it really carefully with that smart controller. It's not easy, because when the controller plays up, you just charge your battery and it then does all sorts of funny things on you. Some of the impacts we've had, we might have pushed some volts a little bit high on a few feeders when the system was meant to discharge, but was charging when it should have been doing the opposite, and we've pushed the volts either too high or too low. Sometimes all that takes is an incorrect setting in a controller. Really simple mistake, or a sensor goes corrupt. You lose comms to it. We've had it happen. And the other challenge with it is the operation of the battery changes from month to month, from season to season. We've got a couple of battery systems, we're logging onto them every 3 months and changing the set points in them, because the voltage through summer on the feeder might sit a little bit higher with all the solar, less load through winter when everyone's turning the heaters and everything on, the volts drop a little bit. And because the battery's responding to that, we've got to change its set point. So it's a dynamic interaction we have with the battery systems through the year. Bottom left, reliability. Keeping the systems online. That can be a job some days, just in itself. Forget about what you normally got to do. Some systems are really difficult to keep online. They can be temperamental, batteries want to trip off, set points want to be silly, but you've got to keep them online, so you've got to manage that. As I was indicating before, the reliability for the systems to run for long periods of time unattended. So a couple of our battery systems, we only turn out to every 12 months. We have comms to them, but for 6 months of the year, we can't physically get to the battery system without a helicopter. We've got to fly, cruising to site, big cost, big money to us. We don't want to do that. We make sure our systems stay reliable and stay on. Another challenge, and Paul, you were touching on this in terms of how the systems operate, being able to withstand what I would call credible contingencies. There are contingencies on the network, contingencies that occur in normal life. The systems need to be able to stay on. So for example, a quick little voltage dip, we don't want all the batteries necessarily tripping off all the time. We might want them to stay on. Or we might want it to go, yeah, I've got a battery trip, but I'm actually going to reduce my output to 0 before I trip off. And the other issue, reliability, when it comes to network support, got to remember some of these comms networks have high latencies. We can't have high-speed 5G comms to every battery system on the network. It's not physically possible. Where we have our Gus units, if we get a round-trip ping of greater than 2 seconds, we're cheering because it's on satellite. So to try and do high-speed control over that comms link is near impossible. It's a 2-second round-trip latency if it's connected. If it's not connected, it could be up to 15 seconds for the first packet to go round. How do we build control systems to manage that? Support. Support is really important from both vendors, customers, and also the utilities. We all need to support each other with these products, and we need to realise support is a long-term effort. It's not something that just lasts for the warranty period or just lasts for the first 3 years. It's something that needs to occur throughout. The other factor with support that we've found with especially our network batteries, remote control. Remote support from the office is really important. You can't be turning out to all these batteries all the time because the financial benefit just goes through the floor really quickly. We're spending too much money, crews on site. People are saying, well, why don't we just install the network again? It doesn't cause us as many problems. I don't have so many crews out. We've developed in-house a model where we monitor all our devices remotely. So we know exactly what's happening down to a cellular level in the battery. So in our Gus units, we have 1,024 cells per system, and I can tell you what every single one of them is doing every 2 minutes of the day. That's the level of monitoring we have. Now, what benefit does that bring from a support point of view? When I have a problem or my system trips off, I can send very detailed event files to my manufacturers. Within 12 hours, they've come back to me with the fault. We've picked up the gear we need out of the store and we're heading to site. Versus turning up to site, trying to fault find the problem, then trying to get on the phone, finding out you didn't bring the right gear, you're back and forward, back and forward, back and forward. You start to burn a lot of money. So that remote support is really important, especially when you're talking about the network. Functionality is important. Are we doing peak shaving? Are we going to try and do solar soaking? What are we doing? How does it function? A really interesting functionality we found that we dislike, a very early battery system would finish its discharge and would then immediately charge at full power in the middle of the peak. Brilliant, I've just fixed the voltage and the loading for half my peak and I've just increased my peak. Now, at that point in time, trying to get the manufacturer to change that setting was almost near on impossible. Now it's a bit different, but they're the sorts of things when it comes to functionality we've got to watch out for. What happens when there is an odd event? We don't want the systems to all charge or discharge. How do we get diversity? If we're starting to put out all these products that are identical, common mode failure. They've all got the same firmware. They potentially all have the same firmware bugs in them. How do we manage that from the point of view of control of the network? Integration of products can be good to the network, but it can also create more complexities. So we've had that as well, where we get some very odd interactions between equipment. And the other functionality is monitoring of the devices. So there are challenges that we've overcome, but wanted to share those with you because they're the sorts of things that from a network point of view, we're having to manage. I'm almost out of time. Some overall learnings from all our battery trials, and this is applicable across all industry, all sectors, is there is a struggle between battery life and network support. I can support the network and keep my voltage really good, but there's every chance I'm ruining my battery life, so I'm not getting my ROI, return on investment. Or I'm maintaining my battery life, but I'm not meeting my network support. How do we find a balance between the two? Kilowatts in does not equal kilowatts out. What I'm saying there is I can support a network and discharge the energy, but I need to get that same amount of energy back into my battery again. How on a weak network where I might be injecting energy for 10 hours a day, I've then got to get all my energy that I've exported back in again. How do we make sure that we're topping our batteries back up and we don't end up with a beautiful case that we always get on our network with some of our batteries? We call it the staircase. We start at 100% on Monday. By Thursday morning, we're flat and the battery sits flat until Saturday. We can't recharge it. We don't have enough capacity on the network to recharge it properly. How do we prevent that from occurring? Because you've just lost your whole business case around why you put your batteries in. I've touched on it a few times, data logging. Data is king for us when it comes to battery systems. Absolutely king. It drives our business. It drives how we manage our batteries. It drives how we're looking after them. Disconnection. We've noticed with a couple of our systems, when there's a fault, it basically runs for the hills. Goes, I'm out of here, trips itself off. It doesn't care how much export, import it's doing, it just trips off. That's a real problem because we send step voltages up and down our networks when these trip off by accident. What we're finding is we need a much nicer situation where they start to ramp themselves down if there's a fault, so that when they do disconnect, you don't see a bump on the network. Now that takes a little bit of integration work between the batteries, the inverter and the overall control system. However, it's much, much nicer to our network overall. So yeah, so in wrapping up, as Paul was indicating, and we still have a long way to go, with network batteries, I think Ergon has shown we can use batteries to support our network. However, it hasn't been simple. You know, we've now been doing it, we're trying to do it for 10 years. We've managed to, I think, crack it with our GUS units, the panoramic down the bottom there. However, it takes time, it takes effort, it's taken resources, it's taken a lot of knowledge. What's more important now is that as an industry, we all work together to make sure that we're moving us forward, we're learning from our mistakes, from our peers, from everybody else, so that as we introduce new projects all the time, we're not relearning, we're not making the same mistakes again, because we're moving so fast in this industry, we need to move forward as we go on. So thank you.
Hello, can everybody hear me? Yeah, so for the avoidance of doubt, I'm not Dr. Nilesh Modi. He has just become a father for the second time, so he's asked me to step in. So look, tonight I just want to take you through some of the applications that we have for large-scale energy storage in the NEM. We're not going to touch on everything, but we're going to touch on some of the key proven areas that we have in the NEM. See if this works. Oh, beautiful. Okay, so look, this presentation tonight is largely a case study on the big Hornsdale battery up in South Australia. But you know, battery storage in the NEM has increased a lot. There are now some really big, important installations at a couple in Victoria at Gunnawara and Ballarat, and the Dalrymple battery as well in South Australia. So we're getting some big storage into the NEM. And today's presentation is largely, I guess, focused on some of the support applications that we have. So one of the big applications, which isn't listed here, is making money. So the strict arbitrage, buying low and selling high. We're not going to really discuss that one there. We're going to more focus on some of the more, I guess, interesting from an engineering point of view applications around frequency control. Paul mentioned an acronym called FCAS. We're going to use that one a bit tonight. And also have a bit of a detailed look at the special protection scheme that functions in South Australia. Okay, so how did we get here? It's a good point. Like most important diplomatic and business decisions nowadays, it began on Twitter with Mr. Cannon Brooks. Asking Mr. Elon Musk if he could do something to improve South Australia's reliability. So just to put this in a bit of context for you, the summer of 2016-17 in South Australia was an absolute shocker for the state. Around September 26, we lost the entire state after a major storm. And then in February 2017, we shed about 300 megawatts worth of load. We asked for 100 megawatts, and the South Australians nicely gave us 300 megawatts to shed off. So that's where we were. This is why it was such a big issue at this time, not just with various billionaires, but also with the people of South Australia and very much the government of South Australia. So Tesla paired up with a company called Neoen. So Neoen are the sort of owners and operators of the Hornsdale system. And they built a battery, which is pretty big, still pretty big by international standards. At the time when it was built a couple of years ago, very big by international standards. So about 100 megawatts and 120 megawatt hours. Basically, NeoN could use the bulk of it, the bulk of the energy that is, for energy arbitrage and also for supplying market ancillary services. But the government basically portioned off a little bit to be able to use for system security purposes. So this will be the special protection scheme that we'll talk about in a little while. Okay, so let's dive into some of those things. So again, the main topics I'm going to talk about tonight are the frequency control applications and the reliability special protection scheme. So in the NEM, we have two types of frequency control. We have primary control, which is sort of fast acting and it happens in relation to large disturbances. And we also have secondary control, which is slower acting. And this is what we're talking about here. This slower acting frequency control is delivered through a control system which AEMO runs and operates, called the Automatic Generation Control, or AGC. And basically what it does is it controls a number of units in the NEM, pulses them up, pulses them down, basically in response to slow movements in frequency control. So if frequency is a bit too high, it'll start pulsing units down. If frequency is a bit too low, it'll start pulsing units up. Now, the ability to deliver this type of frequency control well depends on how well you can actually follow those signals. And when you have a look at this battery, the Hornsdale battery, it can follow it almost exactly. So from a standpoint of delivering this secondary slow frequency control, the battery is absolutely brilliant. And then this says battery up here. You're reading it wrong. It actually says coal-fired power station. That's sort of the more traditional sort of AGC response that we get. So it's not really great. This is absolutely beautiful. So you talk to the guys at NeoN and at Tesla, and they say, you know, we can make the battery do anything. It's just programming, basically. Okay, that's secondary or slow frequency control. We want to talk now a bit about primary frequency control, which is sort of the response that we get to sort of large disturbances. So here we've got a bit of an example, one simulated and one actual. So if you look up here, this green squiggly line here is, sorry, synchronous. So what we've got here is basically a response to a low frequency event. So we get a frequency event, frequency dives down, and then we got the response of sort of various types of things on the NEM. Synchronous condensers. Synchronous condensers were really big about 50 years ago. They're also really big today. Basically, they're just giant sort of motors that sit on the network. They can supply an inertial response. They can also supply a voltage control response. They don't actually supply much real active power. When we get a big bump on frequency, you'll get an inertial response out of the system. So the synchronous condenser will decelerate. That deceleration will provide some energy into the network, but it won't actually provide any sort of sustained response. Here we've got a not too great response of a generator on the NEM, so a synchronous generator. It provides an inertial response. Again, it's a synchronous machine. It'll decelerate once the frequency starts to fall. It'll push some power into the network. And after a while, it'll actually start, the governors will kick in, or should kick in, and start providing some real active power. The red is basically what we'd call a fast frequency response. So being an inverter system, it actually doesn't provide any sort of inertial response, and that is probably one of the main drawbacks of inverter systems, not just batteries, but around the wind farms and solar farms as well. So you don't get any initial response, but a few seconds after the event, we can ramp up really quickly, pretty much to full output. In fact, the battery can go a lot faster than this. We have to sort of pull it back a bit so it doesn't cause too many issues, and provide a nice sustained response, at least over the period of sort of minutes, not over hours. And here, that's simulated. Here we've actually got a real event. Here you can see this time we do have frequency up there. Frequency falling, sorry, frequency rising. And here we've got the response of the generator. So other way around. So blue, response to the frequency falls and overshoots and recovers. And here we've got a beautiful sort of response programmed in to be like a pseudo governor, so it's pseudo proportional to the frequency. So what we find from batteries is that they can provide really good, really fast frequency response, both in the slower secondary control and also in the faster primary control. In addition, they've found to be pretty handy in islanding situations. So South Australia is connected to the rest of the network through a long, skinny AC transmission line, which has a nasty habit of every 2 years or so disconnecting itself. And here we can find that following a disconnection, the battery is actually pretty good at helping control frequency over this islanding period. So we want to try and keep the frequency in as tight a band as possible. Here it is sort of not exceeding 50.1 hertz, which by Australian frequency control standards is good. By international frequency control standards, it's pretty bad. But we can see that prior and after reconnection, frequency control is actually a little worse. Okay, so that's frequency control. It's one of the big applications that we have. One of the other key applications that we have in South Australia for the Hornsdale battery is around the System Integrity Protection Scheme. So what we have in South Australia is we have a long, skinny AC network here connecting South Australia to the rest of the network. We have a little DC link up here, which is sort of invariant to frequency control. What happens, and what we almost happened not long after the February event and almost caused half the organisation to resign, if it had occurred, is that we had a fault up in the Torrens Island switchyard, which disconnected a number of power stations up there. When that happened, you get an inrush of power from the southern states. If that gets too much, you can overload the Hayward interconnector and cause it to disconnect. And when you get that scenario, when you get a loss of generation in South Australia, which causes the Hayward interconnector to disconnect, the normal sort of protection schemes that we rely on to save the network in this case, so our under-frequency load shedding, just aren't able to cope with an event that size. So what the South Australians, Electronet and others helped design was what's called the System Integrity Protection Scheme. So what it does is it detects big changes of flow on the Hayward interconnector and then takes a few basically preemptive steps to try and prevent the interconnector disconnecting. The first one of these, and the one that we're mainly concerned with tonight, is energy discharge. So if you remember that 70 megawatts, I think it's only 10 megawatt hour component of the battery, this is what it's used for. So what it's used is we detect a big power swing on the interconnector. It rapidly injects these 70 megawatts. If the power flow is still too high, we shed some load as well, preemptively shed about 200 megawatts of load in South Australia as well. And the combination of those two things under many circumstances is sufficient to prevent an overload of the interconnector and to keep the system secure. So here's an example of when those two components work well together. Here's an example of when they don't. Okay, so we found, through this system we can sort of give a bit more peace of mind to reliability and security within South Australia. One of the other sort of major impacts that we have, it's not fully exploited yet, but will hopefully be exploited in the near term, is around managing low inertia scenarios. So what we have in the power system is we have a lot of asynchronous generation. which is displacing synchronous generation. Asynchronous generation doesn't provide any inertial support to the NEM. Synchronous generation does. The consequence of this is that we can actually end up with faster rates of change from a power system event, which require faster frequency response. So we have in the NEM now a requirement to maintain a minimum level of inertia, which is assessed every 2 years. And essentially this sort of minimum level of inertia is dependent upon sort of certain system characteristics. And we find that we can actually get away with a lower level of system inertia if we have sufficient fast frequency response to compensate for it. So fast frequency response and synthetic inertia isn't actually a proper compensation for inertia. We still need a certain level of inertia in the NEM, but we can get away with a lower level of inertia and I guess a higher penetration of renewables if we have sufficient fast frequency response in the system. Okay, yeah, there's some numbers up there, so sort of indicating that we can get away with substantially a quarter of the inertia if we have sort of sufficient fast frequency response. Okay, so they're the major aspects I wanted to discuss tonight. So I guess, what didn't we talk about? One of the key and I guess exciting areas that we have for battery storage coming up in the NEM are what are called grid forming inverters. So currently the way that batteries work is that they are grid following, which means that they're not actually able to produce sort of a voltage waveform on their own. There are batteries and there are technologies which do allow batteries to produce a voltage waveform and also to produce some additional fault current. This allows them to sort of operate on a system with no other generation. And what we are exploring is whether we can use these batteries to help us with system restoration. So that's one of the key areas. I guess one of the things, just to loop it back to Paul's presentation at the beginning as well, is that we tend to think about batteries in the NEM as a large scale, the Horn-style battery, of the Gunnawara battery, the Dalrymple battery. But now we're actually looping back and we're starting to look at using some of the smaller scale batteries through virtual power plants in the NEM. And one of the key things that we're looking at now is actually looking at getting some of that frequency control, so particularly the contingency frequency control, the faster frequency control from VPPs. I guess sort of to draw a circle around the presentations tonight, we are now getting to the point where we can actually fully exploit the household batteries to provide the same sort of services that we're getting from the grid level batteries. Thank you.
Okay, thanks to my three speakers. I think you have done a wonderful job. And particularly, we have given a lot of electrical engineering this evening. So if you are not sure some of the terms, you can talk during the refreshment time as well as you can ask some questions. Now I will invite my three speakers to come to the stage. And if you could introduce yourself briefly and your affiliation and ask your question briefly as well. Any question, comments from the audience? Yep, just on that corner.
That's a good question. What are the key performance indicators? That's actually really challenging to give you an exact answer because it depends on what we're putting the batteries in for. And even with our gush units across the 20, they all perform very differently. One of the key indicators that we do certainly have is that they're available. That online, they haven't tripped off, or they're in you could say a ready state. So we haven't dropped a breaker or something like that. Probably the other metric we're also looking at is that an external environment hasn't caused the batteries to derate. So if people aren't aware, there have been a couple of situations where external temperature has caused the battery to derate. So therefore you can't get the output that you need out of it. And probably the other major one is that it performs as expected. Whatever expected means is different for every situation, but that it's not, you're not looking at your control system or your output data going, why am I getting an output spike in reactive power, but it's performing to the planned controller that you've got, and it's doing that regularly, is probably some of the key metrics. I know that a lot's spoken about what's the round trip efficiency and that sort of stuff. In the applications that we have, round trip efficiency actually is irrelevant to us because we're not cycling every day. So a round trip efficiency for us actually is irrelevant because I may have charged my battery today and then let it sit for 3 or 4 days because it wasn't needed and then discharge. But if I looked at energy in versus energy out over those 4 days, I think I did a count one day and I was sitting at, I was consuming more energy. Like it was effectively like 20% efficient. But that's because of the auxiliary services that you need to run to have it online ready to go.
Any other questions or comments? Yep. So, okay.
That's a good question, and it's actually a pretty active question for us. So we get pretty good telemetry from the batteries as to their sort of current charging state and their current performance. I suppose the main challenge for us is not so much the status of the battery, but the future status of the battery. So these batteries are operating in a market. And we need to be able to depend on them for reliability purposes. So we need to know how are you actually going to perform over a day. So if we've got a 10% PoE peak day, how are you going to be charging and discharging over that day so we can maximise our reliability there. Also how we sort of can balance between the frequency control and energy dispatch side of things. But in terms of the environmental components, most of those are pretty good. Yeah, so we haven't had too much of a trouble though in terms of the sort of the main sort of controlling characteristics of the batteries though.
Okay, I think we have, yep.
Right. What do you see as the options for solving the duck curve, and how can you incentivise the owners of batteries to help solve it?
Yeah, so I think there's a couple of approaches. The question for people who didn't hear was how do we go about incenting customers to solve the duck curve? Because at the moment, you know, as I was mentioning, we're just charging in the morning and then exporting like crazy all afternoon. There's a couple of strategies there. It's one of them is just expect good behaviour from the component manufacturers. There's no reason for us to have to charge in the morning if we know what's going on in the afternoon, and we do. That was an illustrative example I showed before, but there's nothing stopping us from being well behaved. And so naturally a lot of manufacturers will move in that direction anyway. And the other one, but your common two strategies that are being used everywhere else are regulation. And one of the trials that we're involved in is around setting network parameters. And in fact, SA Power Networks are doing this at the moment as well, where they're going to start setting export limits. And so if they publish ahead of time that there's an export limit on a certain feeder, for example, then you'll know ahead of time that you're not going to be able to export at maximum at 12 o'clock in the day. And so if you want to drive maximum economic benefit for your customer, you'll have to start shaping your charging profile to meet those published export limits. So I think once the networks become smarter about and start requiring these connected systems to respond to dynamic export ranges and other operating envelopes, naturally the systems, if they want to provide good return on investment, will have to start to get smarter, or they're going to just get tapered off and they won't be able to deliver the proper economic outcome.
Okay, one from here.
My name's Adam Arlandis. I'm with Powerlink Queensland. Just have a question about the inverters that you use with the house batteries. Do you do any like ride-through tests and stuff with NSPs? Because what we're seeing at the moment is that there is shake-off of PV systems when there is disturbances in the grid. That's okay during the day when the load's a bit lower, but what we're worried about is shake-off of batteries in the future when the load is much higher. And that's so are you doing like ride-through testing and standards around that?
So question for people who can't hear was, are we doing testing to make sure that the inverters stay online when there's, say, a harmonic or voltage disturbance on the line when we're potentially providing network support? And the answer is there are standards that we comply to, but actually I think it's an area where industry need to get together with manufacturers as well. It's very difficult for us to test those scenarios with our equipment because you need a virtual network. Actually, some of the university equipment enables testing those scenarios, and it's something we'd like to get into more. And I think some of the standards are actually pretty restrictive. We have to disconnect on certain harmonic disturbances, and there are cases that we see in particularly rural networks where we've got customers that call up and complain because they're running on their backup circuit in the middle of the night and they don't know why. There might be an industrial load nearby that's tripped them off, and they'll reconnect, but it is a problem. And frankly, from what we see, we'd like the ability to be able to ride through more from a standards perspective, and we'd like the networks to kind of lead that, and we'd be happy to get involved.
Yeah, just to add on that, we have a renewable energy lab in electrical engineering, and we have been doing all this testing for different types of inverters according to IEEE 1547 older standard as well as new standards. So if you're interested, we can speak about that during the break time.
I'll add.
And my colleagues are there.
Can I have one more comment to that one,
Yep.
Catherine? So within Ergon, we've done some testing as well. One of the big things that we've noticed is three-phase faults, three-phase to ground, three-phase together, brilliant data. As soon as you go and say I've got an unsymmetrical fault, so even some of the big players, and I mean big players in the market, we can't get data out of them. They do not know how their inverters will perform with a unsymmetrical fault. So a single phase to ground or a high impedance to ground, what happens? And we get blank looks, and that's been right up to their production engineers all the way through. So I think as an industry, we're trying, but there is an education process. There's also an upskilling in both, DNSPs, TNSPs, but also manufacturers to be able to supply that data.
And availability of test equipment, frankly, it's relatively challenging to simulate a fault on a three-phase line, or actually perform it in a safe condition. So using some of this equipment that the university has, as a group, is something we need to do. Yeah, definitely.
Just one last one is to hit the jackpot with that question. If you looked at that incident which happened in the UK, about 500 megawatts of DER tripped off as part of that event, which sort of led to the sort of large under-frequency event rather than a relatively small generation event.
I think there was one more question. Yep.
So we talked about household batteries and big batteries, but we didn't talk about EV. So how we can help with that?
And we're desperately waiting for a government subsidy so that people actually start buying them in this country. But as far as we're concerned, they're just another controllable storage mechanism in the house. There's actually a lot of the EV manufacturers today won't support bidirectional energy flows for their vehicles. Some are starting to. So it's definitely a developing space. They're very protective of their battery lifetimes, but certainly it's something that we're all very interested in doing. And it's just another big battery that we get to move around. So it's pretty exciting, but it's more of a watch this space at this stage.
We'll just take the last one from the back. Yep.
answer that. Yeah. Battery management systems. So the question is, battery management systems, how do we manage that network versus support, battery life, and how have we found the battery systems in Australia? Battery management systems are a very interesting piece of electronics. You can get some very simple ones from some online manufacturers, which is a board that sits on top of your lithium batteries. Don't buy one of those, please. Oh, you beat me to it. Yeah, they have a lot of challenges with them because they're trying to be very broad in the batteries they can support. You go to a vendor supplied system and you pay big money for it, but you hope to get a good quality product. That doesn't always happen either. It does, but it doesn't. So I think the main thing when it comes to the battery management system is to understand its primary purpose in the system. A battery management system isn't there to control the flow of energy in and out of the battery. The battery management system is there to protect the battery and make sure it is safe. It won't catch fire. When the volts get too low, the thing trips off and throws alarms. When the charge is too high, it trips off. If we start to say a battery management system controls the flow of energy, we've got it wrong. The inverter, the higher level control, controls the energy flow. The battery management system sits there to watch the state of that battery. And something else on battery management systems, some of them are designed really well and they have SIL safety and design certification, they have good PCB design, they have redundancy built in. Other ones, some of them we've seen are Arduinos, Raspberry Pi systems. Yeah, let's just say that some of those, as Paul alluded to, don't buy. Just a warning, the cell and the cell chemistry is just as important as a battery management system. A good cell, well manufactured, with a poor BMS can perform well. A really good battery with a poor BMS can perform well. But you put a poor BMS with a poor cell, we're in for some of the challenges you've seen with house fires, etc., going down. So your battery management choice is really important. And the other big important piece out of that is how it integrates with the rest of the system. You don't want your battery management system to be totally separate. It needs to communicate with your inverters and your overarching control. So in essence, your battery management system is probably one of your more important systems in the whole control scheme. But it's maybe something that's underrated sometimes.
Okay, I think with that, it's time to wrap up. So as we promised, we have started to the topic from the energy management to the distribution network, voltage support, and finally to the large-scale power systems of the name frequency support. Three speakers, they have given in-depth descriptions of the problem and some solutions with case studies. So I think it is time to show our appreciation to three speakers. And also I'd like to thank the audience for coming in, and please stay tuned with Energy Initiative. I'm sure more programs will be coming and we'll let you know. Thank you. Please join with the refreshment at the outside of the...
Thank you. Yeah, thank you. Thanks, Stefan.
You guys like your down and then stand in the order that you are on the screen. Okay, this way. Oh no, you're not on the line.
Oh, there. Oh.
Excellent. You're going to feel uncomfortably close. Doesn't look like it on the